All right. Okay, so it's been some time since we have have had our class. Do you remember what we were doing last time? We started discussing capacitors, right?
Yeah.
So we continue from there. All right. Okay, so basically we talked about capacitors and we defined a capacitor as a device that stores charges, right, per unit potential difference. And we'll see uh, essentially what happens is that capacitor does not really store charges, but in fact it stores energy, right? We can talk in terms of charges, but essentially what it's storing is just energy. I'll give you a hint. If you look at this diagram that we did for discussing capacitors, we saw that what happens is as we connect the battery to the capacitor, the charges start flowing. So the positive charge leaves this plate, so it becomes a negatively charged plate, as you can see, and the other plate gains that charge, so it becomes overall positively charged plate. Now you can see that the net charge on this capacitor is zero, right? So the net charge on the capacitor is indeed zero, and in fact that's why it is not really storing any charges, but instead it is storing energy, right? And it's storing that energy because when we attached the battery to the capacitor, what happened was work was being done, right, in charging my capacitor. By charging the capacitor, I just mean that attaching a battery to it, and then charges started flowing. So it's essentially the energy that is being stored. And we can talk about this energy stored in a capacitor. Let's actually, in fact, that's something that I wanted to just clarify before I proceed further. Uh, and then we talked about how much of a charge can we store in the capacitor. Now, again, we can talk in terms of storing charges, but actually, it's not the charge that is being stored, it is the energy being stored. And so that energy is just proportional to how much charge I can store. So the more charge that we can assume to store on the plates of the capacitor, the more energy we are storing, right? So this amount depends on the type of capacitor, what material capacitor that we're using, and it depends on, by a type of capacitor, I mean these plates of these capacitor, and if it's a large capacitor or a small capacitor. And the dielectric medium is this region between the plates that is our dielectric medium. It can be air or any other insulator, right? So that the charges are stored on the plates. And from there, we saw that the more potential difference there is between these two plates, the more charge I can store, because the potential essentially is just if there is more positive charge over here and less negative charge, less negative, so that increases the difference between the potential of these two plates, right? And so if that potential, that's what potential difference is, and if that difference is increased, what is happening is charge, the charge being stored is being affected, right? And that's what causing this potential to change between the two plates. And that's why we see that the charge is directly proportional to the potential difference between these two plates. And that gives me a proportionality relation from which I can write a mathematical expression that says that the charge is equal to some constant times the potential difference. Now, this constant is what is defining how much charge I can store on my capacitor. And hence, it's called the capacitance of the capacitor, right? And so the capacitance is then just defined as the charge stored on the capacitor per unit potential difference between the plates of the capacitor, right? And from there, we just worked out the units for capacitor. Charge is coulombs, potential difference is volts. So it's just coulombs per volt, which makes sense. How many coulombs of charge I can store per unit potential difference, as in per unit volts. And that is just given a name as a farad, right? And this unit, 1 farad, is a very large amount of capacitance, right? And you can get an idea about this thing if we try to figure out the capacitance of our entire planet, right? And we can do that. We can definitely do that. And it might sound weird at first that our planet, the Earth, has capacitance. It's any isolated body, isolated meaning isolated from the environment and any other forces and all of these things, it will have a capacitance, right? It will have this property of capacitance, and we can. The only thing is that it should be a conducting body, right? So just a point over here is that any isolated conducting body will possess or will have a capacitance. So what that means to say is that any isolated conducting body is a capacitor, right? Now, from just basic AS physics, when you study these electricity in AS, we define the potential at the surface of of a sphere, right? So the potential at this surface is worked out to be a charge divided by 4 pi epsilon naught times r, right? And this is the potential on the surface of the spherical body. So we can assume that my planet Earth is a sphere. It's a good approximation. And then we can work out the capacitance of planet Earth. So suppose that this is my planet Earth. We know that the radius of our Earth is it's approximately 6.4 into 10 raised to power. Is it 6? I think, yeah, it's 6 meters, right? So in meters, this is the radius of planet Earth. And now, if I want to work out the capacitance of Earth, so I'll just, let me just give it a heading, capacitance of Earth, right? And we can do that because we know capacitance is just defined as charge stored divided by V, right? That's the potential difference, right? Now, all you have to do over here now is just put in this value for V in this expression, and that gives you C is equal to Q divided by Q over 4 pi epsilon R. Q goes with Q, and this just becomes 4 pi epsilon epsilon naught, which is just the constant permittivity of space, and R is the radius of the Earth, which is 6.4 into 10 raised to power 6 meters. And the permittivity of Earth, this thing is, I think it's 8.9 or 8.85 into 10 raised to power minus 12, right? And now if you do the math, this gives you a capacitance for the Earth, which is 700 into 10 raised to power minus 6, which is 700 microfarads. So are you following along up till now? There is something in chat. What does E not mean? I'm sorry. It's very hard for me to keep track of chat as well while teaching. If it's possible, you can unmute yourself. And if you have said if you have asked a question in chat and I am not getting to your question, just unmute and let me know that there is a question in chat. Okay? So I don't mind. You can stop me anywhere and ask questions. Is it okay, Hasib? This epsilon naught is just the permittivity of free space. How much? So in space, it defines the permittivity. How much I can permeate my free space? As in, you define speed of light from this thing. So it defines how fast can things flow in space, right? This constant defines, roughly speaking, it defines how fast things are allowed to flow in space, right? Does that make sense? I cannot hear you. Is anyone speaking? Okay, no. Are you following along up until this point, everyone? All right. Okay, so yeah, coming back to this thing, the capacitance of the entire. Can you write the proper definition of it? Okay, so it's hello. Can you hear me? Yeah. Okay, so I don't know the spelling of permittivity. I think it's PERMITTIV. It's permittivity of free space, right? And it's denoted by this symbol. It's called epsilon, and this little O is a naught, epsilon naught, and so it. Let me write define it as okay. So it defines to how much I can permeate my free space, or the in terms of capacitance, you can say that it defines the distribution of capacitor or of capacitance in the entire vacuum, right? So free space as in vacuum, right? Free space just means vacuum, where there is no potential in that space. And mathematically, it's epsilon naught is 1 over mu naught c squared. Essentially, it's this thing that c speed of light is 1 over square root of mu naught epsilon naught, right? This epsilon naught and mu naught defines the speed of light. Mu naught is just a constant. You don't have to go into its detail. It's just a constant that comes from magnetism, and epsilon naught is the permittivity of free space. And it's essentially just a constant as well, just as the speed of light, and it more or less defines how fast can so I'll say things, but like any charge or by things I mean charges, current, and all these type of things, right? Are allowed to flow in free space. So when there is nothing hindering the motion of these things, right? Okay, so does it make sense, or do you want me to go into more detail? Because to go into its detail, I'll have to, you can talk in terms of electric fields. It's essentially, when I say things flow, I'm talking about charges that are flowing, and charges, whenever you have a charge, you have electric fields, right? Now, we know that, so for example, I'll give you a very quick example with a positive charge. We say that the positive charge has these electric field lines that are radially outwards, right? Now, these electric fields are moving through vacuum, or you can say through space, right? These electric fields have to move through space. That's why they're going in the outwards direction from this positive charge. So epsilon naught is just the ability of these field lines to propagate into space, to move in space, right? And it's defined by a constant 8.8 into 10 raised to power minus 12. Okay, so Hasib, does it make sense? So I'll write it down as the ability of field lines to flow in space. All right. Okay. So anyways, coming back to this thing, it's 700. So we basically computed the capacitance of an entire planet of Earth, and Earth, mind you, is a very big object, and yet the capacitance is in micros, right? 700 microfarads, and it's it's not surprising that the capacitance is not small. It just tells you how big of a capacitance 1 farad is, right? So 1 farad is a very big amount of capacitance. So even if we talk, that's why we have our capacitors, which have their capacitance on those capacitors are defined in microfarads, right? So 1 farad is a very large amount of capacitance. Okay, so now we can talk, because we are familiar with this equation, Q is equal to CD, right? The equation for capacitance. We can move towards capacitors in the arrangement of capacitors, really, right? So we'll first talk about capacitors arranged in parallel way in a circuit, right? So you're making a circuit of these capacitors, and you're arranging these capacitors in parallel. I'm sure you have worked with these circuits using resistors, and it's as we'll see, as it turns out, the capacitors behave exactly in the same way as a resistor when we talk in terms of its mathematical equations, right? So we'll see what I mean by that. Suppose that we'll draw a diagram of a capacitor. So we'll just attach a battery to the circuit, and let's try to draw capacitors arranged parallel, right? So this is one. This is another one. So yeah. All right, so this is C1, C2, and C3, while this is a battery with positive and negative charges, which would be the reason for the potential difference in the circuit. And if I'm connecting this battery to this parallel capacitors, what is going to happen? Charges are going to start to flow, right? So a charge will start flowing from here. So it will go like this. So essentially a charge Q flows this way, and it splits into three parts. So Q1, we'll say some Q1, some Q2, and some Q3 goes in these respective C1, C2, and C3 capacitors, right? Now, we want to write down a mathematical equation that defines the total capacitance of this circuit, right? And to do that, we'll use what you have studied in AS, Kirchhoff's laws. Kirchhoff's, some people call it Kirchhoff, some people call it Kirchhoff's, whatever it is. So we're going to use Kirchhoff's laws. First, let's try to understand this potential difference, right, across each capacitor. So Kirchhoff's law, second law, is essentially conservation of energy. It's telling you about the conservation of energy, right? Kirchhoff's second law. These laws are just going to help us and write down the mathematical expression for the total capacitance, right? So Kirchhoff's second law just states that the sum, the algebraic sum of every case, it's just telling you that every capacitor is going to have a same potential difference across those capacitors, right? So see, all these capacitors will have the potential difference defined by the battery, right, which is V. So from Kirchhoff's second law, we can write down an equation that would say that every capacitor has equal voltage across it, right? And so that helps us in establishing this equation, Q is equal to CV. So now we know that V will be a constant for all capacitors, a same constant, so we can factor that out. Let's see what would be charges, right? What would be a Q? So essentially what I'm trying to say is, so we could have written it as Q1 plus Q2 plus Q3 is equal to C1 plus C2 plus C3 multiplied by V1 plus V2 plus V3. But we see that according to Kirchhoff's second law, the V's will not be written like this. They'll just be same for every capacitor, so it will be just a V, right? So it's C across C1, it's V, across C2, it's again V, and across C3, it's still V. Now, to work out charges, we'll use Kirchhoff's first law, right? It's also called Kirchhoff's current law. And Kirchhoff's first law will help us to write down what's happening with the charges. So we know if I take a point, current flowing into this point is exactly equal to the current flowing out of this point, right? That's what Kirchhoff's first law, or the Kirchhoff's current law, describes, right? So it says that the total current that enters any junction is exactly equal to the total current that is leaving that junction, which means that no charge is lost, right? Because current flowing is just charges flowing, and if charges that flow in are exactly the same as charges that flow out, means that no charge was lost in this process. And this is just the conservation of charge, right? Charge is conserved. So Kirchhoff's these laws are called Kirchhoff's first law and second law, but essentially they're just conservation of charge and conservation of energy. right? So what that tells you about this situation is that according to this Kirchhoff's first law, the total charge that flows from this battery is the sum of the charges on each of these capacitors, right? Because no charge is lost. So whatever charge, this charge Q that I'll write it over here, was flowing, started to flow from the battery is equal to the sum of Q1 plus Q2 plus Q3, because no charge is going to be lost. So total charge Q is just Q1 plus Q2 plus Q3, which means that we can write down our charges Q as the sum of Q1 plus Q2 plus Q3. So this part is completely valid. And finally, using this information, I can rewrite this equation Q is equal to CV as Q1 plus Q2 plus Q3 for Q, and C is just C1 plus C2 plus C3, right? It's the sum of the capacitors. That's what we want. And because potential difference is same across each capacitor, we'll just multiply then this by that potential difference that was coming initially from the battery, right? And this gives me the total capacitance if I compare this equation with the first equation. So I'll write it as first and second. Comparing a second equation with first equation, you can equate them, and the V, which would be common on both the sides, would cancel out, and it would give you C1 plus C2 plus C3 as the total capacitance of capacitors placed in parallel. So that's how you can work out the total capacitance in the parallel arrangement. You'll just notice that this equation is almost similar to the equation that you have for resistors. Actually, if I do capacitors in series, it's only then when you can understand that, because in capacitors in series, it will come out to be 1 by C1 plus 1 by C2 plus 1 by C3. And we'll do this, but let me just say it anyway. So this would be the total capacitance. This would be in a series, and it's just the reverse of how you work out the total resistance in resistors, right? Because in resistors in series is how capacitors behave in parallel. So that's just it's just the inverse of how resistors behave, right? So before we move on to series arrangement of capacitors, is there any question in capacitors in parallel arrangement? Any question? All right. Okay. So let's see. Let's actually use the next page. Now let's quickly talk about capacitors in series. So I'll quickly draw the diagram. You're all familiar with the idea that series arrangement is a sequential arrangement of capacitors. So it will look something like this. Right. So this is the battery, which means that this is providing the potential difference, and the charge starts flowing like this. So this is the charge Q that would flow into these capacitors. This is C1, C2, and C3, right? So this is how we'll have our capacitors in series. Now we know that in series arrangement, the potential difference does not behave as how does in the parallel arrangement. So in the series arrangement, Kirchhoff's second law, I'll write it over here. So from Kirchhoff's second law, which states that the essentially states that the energy should be conserved. The energy can only be conserved if the potential difference across the battery is equal to the sum of the potential differences across each of these capacitors, right? So it states that the total potential difference is V1 plus V2 plus V3, where V1 is associated to C1, V2 associated to C2, and V3 associated to C3, right? Now, if the potential difference is distributed in this way, when these capacitors are in series, that's when the energy conservation is not violated, right? Not violated. So now we can use the equation for capacitance, which is just Q is equal to C times V, and you can rearrange this as V is equal to Q by C, and use this V in this above equation. So it would become Q by C is equal to Q by C1 plus Q by C2 plus Q by C3, where this Q by C1 is V1 according to this equation, and similarly Q by C2 is V2, and Q by C3 is V3. So this gives me 1 by total capacitance is equal to 1 by C1 plus 1 by C2 plus 1 by C3. And this equation is the defining equation for capacitors arranged in a sequential arrangement, which is just the series arrangement of capacitors, right? So this expression formula that you have for resistors in parallel, right? So the combined capacitance of multiple capacitors in, if you look at the parallel arrangement of capacitors, which was this equation, the combined capacitance is smaller than the individual capacitors, right? So this equation. That's what this thing is telling you. So is that clear? Any question? In series, Q is same overall, and in parallel, V is same overall. Right? Yeah, exactly correct. Right. So these it's a statement that you're saying, and this statement is derived from Kirchhoff's laws, right? First law and second law. So for the energy to remain conserved in this type of a circuit, the potential difference has to be the sum of the potential difference across each capacitors. So yeah, that's good. All right, so we can do a problem uh, related to this thing, capacitors. How much time do we have left? We have 1 minute, 40 seconds. I think that would not be enough to complete the problem. So we'll in the next class we'll do an example, and we'll talk in detail about this thing where I said that in capacitors it's really the energy that is being stored, and we'll see what how much energy can be stored in a capacitor, right? We'll derive the mathematical expression, and we'll discuss that in the next class. class, and we'll be done with electric fields, right? The A2 electric fields will be done with that, and we'll start magnetic fields or magnetism. Right? So less than 1 minute. I guess I'll end the meeting. If there is any question, feel free to ask. By the way, sometimes I might forget to upload the notes that we are making in class. So just let me know in the on WhatsApp if there are some notes that are missing, and I'll upload them. Okay. So at this point, I don't remember if I've uploaded the notes from last chapter. So you can let me know in the group. All right. So okay, perfect. So we'll see.